Oh, yeah, you're gonna hear introduction. So I think you should know. This to me, I just got elected fellow like that.
Yeah. Okay.
So, sorry, so finally it's like solid. Got it.
That's very good.
Yeah.
Okay. Well, let me start introducing Dr. Michael Pettit from the Talent Development Laboratory. I met him when he got his PhD in Austin, in the chemistry department. He had great professors there, except one, but he got through the PhD and then he got to become professor in the University of Houston. He got a career working, and then he moved to the Alamos, when he's a leader group. He part of SILT also, and he has been very fruitful in many things, Raman and many other things like in speak. So and then Michael just got elected as a fellow of the American Association of Mechanical.
Yes.
So we welcome Dr.
Yes, thank you. Oh, I have to click on this one. Hold on.
Keep me on your.
Okay. Wait. Go away.
Yeah.
Oh, I think we might need to.
You can see the mouse.
Yeah, got it. Okay. Use your pointers up. Okay, so yeah, thanks for inviting me to come to give a talk, Miguel and Gabe. I've been really impressed with what I've seen today so far, and I'm going to talk mainly, so we'll show a little bit about the end use applications of some of the work that we've been doing, but I'll talk mainly about some of the characterization techniques that we've built. I love building instruments. We love pushing the limits of what we can do with certain instrumentation techniques like transmission electron microscopy, and that can be useful for a lot of end-use applications. And then I'll give a talk at the end just about what do we as Center for Integrated Nanotechnologies do? How do we work with universities so that we can increase collaboration with NAU? One of the things that is really important for us in our next renewal cycle is increasing participation from the universities that typically don't send us a lot of student users and professor visitors. So I'll talk at the end about that. First, what I'm going to start the talk with is I do a lot of work in two-dimensional materials. They're useful for real applications, right? They're useful for catalysis. They're useful for us, optics. They found themselves as anti-corrosion barriers in Samsung's screens, graphene's in those now. And they have real applications. I use them for a test platform, mainly so we can push boundaries of what we understand and don't understand about model physics systems. So I use them as a platform for advanced material science. I'll show you some characterization. There are patents that have come out of this work that are useful for industry. We use these as ways to push boundaries on materials because, for example, if we're doing electron microscopy, you need a thin, transparent material of a known thickness to quantify techniques. If we're doing things like Raman spectroscopy, we need to be able to model the materials in density functional theory and to come up with the interaction mechanisms to model what the phonon bands are doing with things like strain. And so they're a good overall material system to test things. And then we can use them for real problem areas that we're interested at the lab, which is mainly falls along the lines of metallurgy, which is a much messier system. So in my lab, we do optical characterization and we do structural characterization. I'm starting thermal characterization back up with we got a DR funded down the PIO, so I'm super happy about that. Lets me work on one of the things that I've been working on for the past 20 years. But I'm not going to show any thermal characterization results here. And then at the end, we'll talk about Center for Integrated Nanotechnology. There's two types of proposals that we have. So our proposal window just closed at the end of March, but we have a new proposal window open in September. we have a mechanism called rapid proposals that are accepted any time of the year. I always encourage people to submit those, and kind of the thinking behind those is like, let's say you wanted to wrap up a paper and you need cryo electron microscopy to wrap up that paper, or the reviewers asked you for that technique. That's a perfect justification for a rapid access proposal. Because then it's going to come out, it's timely, like you have a reviewer timeline that you need to submit that by, and those we usually approve within a week or so. But the time frame and the scope of those projects are much smaller. But we like to work with you guys. If you reach out to our scientists, I think you'll find them to be pretty responsive, unless we're just really busy. So 2D materials as a platform, what are they good for? Why are we interested? I chose 3 interest areas that align with the work of SINT and that align with my own personal interests. One is photonics. With 2D materials, you can go basically all over the spectrum from infrared all the way up to ultraviolet. You can even have terahertz down below millimeter length scale in wavelength. So they cover a lot of application areas. Industry, they care about 1550 nanometers. That's what the industry cares about. But for me, for probing physics, I'm interested in ultraviolet UVC, and I'm interested in infrared as well. Quantum, 2D materials have come a long way in maybe the past 8 years in color centers for the 2D materials. So one is they have this valley degree of freedom, and you have different spin orbit couplings at different valleys at different points in the Brillouin zone at K and K prime. So that's one area for topological quantum, but for topological quantum, there's some better materials out there. For color centers though, they're really unique because they're surfaces. So the whole material is a surface. You don't have the color center buried inside of, for example, diamond, or inside of silicon carbide where you can't get to it. It's actually at the surface. So if you can make it in a certain location, you can have very nice sharp emission peaks. All of the early work was in the visible, but we're not pushing into the infrared. You can have very nice peaks, and you can think of these like a color center that you get in diamond, an atomic defect that emits single photons because of the electron energy levels are quantized. So this area has progressed a lot in the past 8 years. And then for electronics, the whole push that we're trying to do with Chips and Science Act that's come out recently. There's no formal call yet, but we're preparing for it. 2D materials is a part of that. And the way that because they're semiconductors, most of them. So the way that we're arguing these materials into Chips and Science is Intel is going to make things with silicon. Samsung is going to make things with silicon. We are going to make things that are advanced materials that might be beyond horizon. And if you want to know how good you can make things with silicon, I just heard a guy from Samsung to be my postdoc. He was showing me 3 nanometer channels in epitaxial silicon. That's what they're making now, 3 nanometers. So silicon is at the limit. Like when they say it's at the limit, it actually is at the limit. So Chips and Science Act is interested in industry. It's mainly industry that's coming through Department of Commerce. But then there will be a science component of it, and 2D materials will be a part of that. So for optical characterization, just to give you an idea of what we do in my lab. So I have a system. It's basically the fancy version of what Miguel has in his lab. It's a Hariba LabRAM evolution. And then we just chop it up and we put a bunch of parts and filters and stages and stuff on it to do different experiments. Mainly with relation to the SINT program, we're looking at quantum materials at 4 Kelvin. So we do a lot of cryogenics work with liquid helium. And then we can do things like, for example, in this slide, we can do things like correlated electron microscopy, where we have special holders that we put the TM holder into the Raman system, because we're not, we want our transmission electron microscope to be very good for a transmission electron microscopy. We want our Raman system to be very good for optical spectroscopy. And so putting those two together in one system is kind of not what our mission needs are at this point. So what we do is we do correlations. So how can we correlate those two? So we do things like build special stages We have very good machinists, and then we can do correlative property measurements. So as an example of some of the end-use applications of what we come up with, this is, okay, so I'll just read off what this is on the top. So this is isotope engineering of 2D materials, and this is a tungsten selenide bilayer. So what we wanted to do is, I'm a phonon guy, I'm interested in vibrational changes. Best way of changing vibrations, change the mass of the system, right? It's a spring damper system. By changing the mass of the system, you get different vibrational energies. So you can think of it like this: like if there's two bonds and the atoms get heavier, then it'll move towards a lower energy. If at the same time, if they stay the same and it moves to lower energy, it means that you're changing your bond strength. So for this, it's same material. This is an indirect bilayer tungsten diselenide. It has in plane and out of plane Raman modes. That was our motivation, is looking at isotope changes and seeing, can we see changes that aren't expected in those spectra? So no surprise, Raman spectra is exactly what we would have expected. Things change with mass as the square root of mass over the average mass. But what we didn't expect is the big changes that we saw in the photoluminescence over the entire temperature range from 300 down to 4 Kelvin. This is something we measured with our system. So it's useful for both things, for photoluminescence and for Raman H2 degradings. But we measured a 4 millielectron volt shift in the band emission. So this is band plus exciton binding energy. So 4 millivolts over the entire temperature range doesn't saturate at low temperature as you would expect for something that was mediated by defects. And then when we started looking closer into this, you can see it's 4 millivolts across the whole temperature range. When we start looking into this, what we started seeing is that you should get this kind of change if you have band gap renormalization. So ARPES, we didn't measure ARPES, but ARPES measures band gap renormalization. That's what it's measuring. So we see this change is a direct effect of that band gap renormalization that comes about because of this isotopic shift. And this is small, right? This is going from natural to 186. So it's a little over 1 neutron that we're changing. But it was pretty significant, and we were pretty happy. Obviously, 4 millielectron volts not going to be that interesting for industry, but for us, from a physics perspective, this was very interesting, and we like to say that we beat Oak Ridge to doing the first isotope engineering in the 2D materials. And it's a model system. It's great, and you can do these kind of measurements with only a couple 100 milligrams of materials. So the next thing that we use the 2D materials for, and we're pretty good at this now, is creating on-demand single photon emission centers at scale. This is what we've patented. And there's a lot of groups working in this area now, and we collaborate with them at Los Alamos. But the idea is, so isotopes change band energy in a certain way, and we understand that pretty well. But what we don't understand is, how does strain change the local atomic ordering? So this is epitaxial tungsten diselenide. The material, we got it from Penn State, from John Redwing, and there's twins in the material. It's disordered. It's not monolayer. The new samples they give me are monolayer, but this, when they were setting it up, this is not monolayer. It's pretty thick. It has emission at about 1.5 electron volts. And it shouldn't be able to be changed by strain. So we said is, let's take this thing and let's strain it. So the way that you strain it is you have to put on something sharp. And you put on something sharp and it conforms and it bends. And if it's too brittle, it'll break. So we made the sharpest tips that we could make. We made this in the clean room. And this is just a very simple way to make it. You start with a big square, but it better be a square, a super square. Like, it better be as square as you can make it. And then you just put it in hydrofluoric acid and it makes a super sharp tip. Then we put the 2D material on top of it. And what we see when we're looking at optical emission here. And what we see is from the tip, so the measurements that I'm showing here, we did this in Wright-Patterson. So the emission coming from the tip is always in the 600 to 800 nanometer range, is very sharp. It's in the microelectron volts line width regime. It's close to transform limited. It saturates, right? We see some saturation behavior here. And importantly, when we look at the anti-bunching, this is like the kind of measurements that astronomers do to tell what kind of light's coming from stars. We basically take the beam, we split it into two paths, and then we look at the arrival time at the detector. So if you think about it as if you have a car and you tell the car turn left or right, and it goes to 1, it'll go to 1. So at 0, it'll be a dip. But if the light is if the light is coming out randomly, then there could be 2 cars going through at once and both go to the same. So normally in normal light, you'll just see a flat line. But we do these kind of measurements. This is with continuous wavelength light, so we'll see a dip. This is called the HBT dip, Hanbury-Brown twist interferometry measurement, and we get it below 0.5, which is the definition for single photon emission. So this is great. We were not the first to do this, which is why this is not in Nature and it's in APL. There's a very good APL paper, but we're very proud of this work, and it gave us the techniques to move towards something that actually did go higher in a whole line of research. So for doing this kind of work in the infrared, at SINT, we have a staff member. His name is Han Toon. He leads the infrared quantum optics lab, and he has the ability to characterize these in the infrared. You notice I was showing most of the 2D work was in the visible one. That's by chance. It has to do with the band gaps of the materials. Usually they're within the visible range. It's also because most of us can measure things in the visible relatively easily now. But in the infrared is harder. So Han has the setup to do that. So what we did was we got a material with a smaller band gap. It's a little less stable. And this is molybdenum telluride. And we, one of our postdocs made little polymer pillars. It's not hard to make. They're maybe 200 nanometers diameter, 50 nanometers in height. And then he put molybdenum telluride on it. So nothing new by any stretch of the imagination. It's just the material was new. It's not super stable. It's hard to work with. But he was able to put it on very quickly. He did dry transfer. He did not do this inside of a glove box. We do have a glove box with a robot that you can transfer 2D materials, but he just did it by hand in air and went straight to the measurement chamber. And we found that you could actually change the emission lines from their normal exciton and trion states here, all the way out. The sharp lines are always in the like closer to the band edge here, but you could also get broad lines out to like 1550 or so. So what we found is with the my technique that's super sharp, everything's kind of broad, but with these nanopillar techniques, you have things that are sharper. The only problem is because you can't make a circle, an exact circle. You can if it's bigger, but these are like 200 nanometers, so you're not going to have it perfect. The polarization that comes out of these things is always going to prefer one particular orientation. So you'll get what's called you'll get this subband splitting if you look at this, if you looked at this at higher resolution or higher spectral resolution. But you can see the HBT dip here. It's even lower than what we did before. That's because the well, like the separation from band edge to defect is higher. So you're getting very good quality single photon emission. Basically put 1 minus this value, and that's your degree of single photon purity. So this is like was it 82% purity. And then on the other end, if we do this with pulsed light, so if we use light pulses to do this, then at 0, it's also 0, but then these are just the subsequent pulses hitting the detector. So this is with, I think this was with a megahertz rep rate. And you can see it's deterministic in that these pillars were made in an array on the substrate. And then when we look at the in-gas CCD. We put some filters on it and then just image the whole thing and see where wavelengths beyond a certain, I think this was wavelengths beyond 1300 nanometers, where those spatially line up. They match up pretty well with where these nanopillars were put on. So we were pretty happy about this as a proof of concept that you can do this same kind of work in the infrared that's relevant to industry. So another way that we've been able to do this then is, and this is in review now, is it's been in review for a while because the corresponding author wants to get it into one of the Nature journals, and you guys know if you do stuff in Nature, you have to fight forever. It's been since 2022. But we did this with interlayer excitons because we did, this is air stable, it's MOS2 tungsten selenide. We said this is going to give us a longer lifetime. It's much harder for the excitons that are split between the layers. So if you have a hole living here and an electron living here, it's harder to recombine those. So those will have longer lifetimes, and they'll be more relevant to, one, to make it easier for us to measure, and then also relevant to industry because they want things that are more stable and that have longer lifetime. The longest lifetime we were able to push previously was about like 10 nanoseconds, and then we're getting about 20 here. And then the state of the art in this field for just regular excitons is about 100 milliseconds. So you can get very long lifetime excitons here. The new thing that we found, and this is some Raman showing the strain. This is a strain mapping that I do with my system. So you can see we're diffraction limited. Peaks line up exactly where you put them. This is where the layers overlap with two of the 200 nanometer diameter pillars. Everything matches up perfectly where we expect it to. Strain, we said, I think it was about like 0.27%, and it's tensile strain. When we're on top of it, you go to a lower phonon energy. But interestingly for us, G2 is even better because the lifetime's longer. So those single photons, they don't have a chance to diffuse and to recombine. So the ability to keep the defect isolated from the host is much better in this system. And then temperature dependence, it's not great, but we get results at 77 Kelvin, near 77 Kelvin that are still below the 0.5 G2. With our early work, we could never get anything to work above 5 Kelvin. It's like above 5 Kelvin, you don't see anything. So we're pretty happy. We're pushing the temperature up. That's just because you're making the difference between the defect energy level and the host level larger. You can see this is a pretty large area, but mainly because this exciton, we don't have the recombination mechanism in one material because they're separated. This is a hybrid band, this gamma band, hybrid band that pops up. Because they're separated, then it just keeps the system much cleaner. And so this we're really happy about as well. The energy scale here, it's still in the visible near infrared. It's not at 1550. It just has to do with the differences in the band edge, but it shows the principle works for interlayer excitons to increase the phonon purity. Yes. Yeah, because for these, they're so touchy. What we want to do is we want to do it with TM. That's what we want to do. But it's so touchy. This is a good example of this. It's so touchy that you want it on a substrate. So I mentioned in the beginning one of our motivations that you have value degrees of freedom in these 2D materials. So the next thing that we did, and it's still in review as well because it's in one of the other Nature journals. And so we're fighting, and the reviewers say, you know how it is. but we think that, I mean, in principle, they're right. They just don't like the theory. But I'm not a theorist, and I respect the guy who did the theory, so I say we'll just keep fighting. But we said, okay, now what if you can break those degrees of freedom with a magnet? And so Hantoon led the DR. Our DRs are our big, like $5 million projects at Los Alamos. He led the last iteration of the DRs, and his DR was based on proximity effects. So proximity effects are take this 2D material, put it on a magnet, a thin magnet. And the reason why you do that is because you can have effective fields in your material above 200 Tesla. It can be very, very high. So you're going to split the bands. In this previous work, I think this one I cut out the magnetism, but this we saw small shifts when we were doing things at 8 Tesla. So it wasn't great. It was like there were shifts, there was Zeeman splitting, but you can get much higher effective fields if you put it directly on a magnet. So we're using a 2D magnet. We got from some collaborators. You'll notice a theme. If we can't do it ourselves, we collaborate. And we got this from some of our collaborators. It's NIPS3. We can work with it much easier than chrome iodide. I try to stay away from that kind of stuff, and chrome, like the chrome halides that have really high fields, but you have to do everything in a glove box. This you can do in air. We got NIPS3, exfoliated it, exfoliated tungsten selenide on top of this, monolayer tungsten diselenide. And then one of our staff members who's really good at atomic force microscopy punched this with an AFM tip. So you're creating an inverse trench shape. So it's kind of an inverse shape. And so you'll have the same kind of bending strain within this defect structure. We didn't invent this. Barry Yonker at Navy Research Lab was the first one to show this kind of work. He did it with polymers. We're doing it with magnets. So the difference with magnets is now you have high field. So what we think is happening, and we get very nice G2, difference with the previous work is it has circular polarization. So that's why we want to keep it in the high impact. That's why we want to keep it. Ideally, I would patent this, but I think we chose for publication first. And we have a very, very nice circular polarization that doesn't depend on the incoming excitation. So there's no memories coming from the material itself. But we think for that is NIPS3, the magnet is an in-plane antiferromagnet. The structure is just in plane. It has different domains. It's hard to see in the way that the theorist plotted it here, but these arrows there's one domain that's red arrows on the bottom, and then one domain that's blue arrows on the top going to the right. And what we think is we're disturbing the in-plane orientation of that magnet with the punching, because we're punching it with an AFM tip. These are like 1 or 2 microns. You can clearly see them in optical microscope. But we're disturbing that, and that's creating an out of plane magnetic field that has proximity to the sample that causes that defect. Now, where that defect lies, we don't know. So the postdoc, we spent a lot of time with him on this, and he came up with a nice cartoon of just showing it could be from here, it could be from the edge, it could be from somewhere else. We don't really know, but we usually get 1 or 2 defect lines that come out of this. The best circular polarization sample we had 4 defect lines coming out of it. So there can be multiple, but the process by which we did this and the conclusion that we take out of it is still along the lines that strain is important. And then just to show, go ahead.
Can you estimate how strong the local field, magnetic field?
So we asked the postdoc to try to do that with the Zeeman splitting, and because there's a G factor and you can try to back it out. I haven't seen those. I think he wasn't able to accurately calculate it. Yeah, which is why we always and we can't measure it with MFM because it's too distorted. So we for that we don't have a good answer for that.
It wouldn't make any sense to put it in this context.
Oh yeah, they did this. The highest that we can do this is 8 Tesla. So this they did it at 8 Tesla, but I haven't seen like he never showed me that. You think if you could do a sweep and you could find out where the 0 point is, but I didn't see that. I think it's just I think it might be just that it's too high so that the fields we're putting on it aren't able to look at it. Now, if you want to go higher, there's a way to do this measurement in our National High Magnetic Field Laboratory pulsed field facility, which is a user facility at Los Alamos, they can do these measurements at 60 Tesla. But for this, we just stopped there. But yeah, that like knowing, no, and they blow up. Yeah, they do. But in principle, the theory is it should be in the hundreds of Tesla. Yeah. And then just to show the characterization that I do, so this project is led by Hangtun, but the characterization that I do is we're looking at what is the difference between these punches in terms of the vibrational spectra of the NIPS3 and off of the punch. And I personally didn't pick up a lot of strain. There's NIPS3 peaks and then there's ENA peaks from the tungsten selenide. This is a Raman spectra, but I did see a big difference, like a measurable difference in the magnon intensity. So magnon intensity, if you go below the Nel temperature, you'll be able to pick up magnons, which are the collective magnetic oscillation. So much like when you're doing electron microscopy, analytical electron microscopy, and you're looking at plasmon peaks in eels, you can see magnon peaks in Raman spectroscopy. And it was much stronger by at least a factor of 2, obviously averaged over the sampling area on the areas where we did the punches. And these measurements took a long time, so that's why I don't have a map, because you're drifting and stuff. So you're trying to optimize the difference in how you're collecting the signal versus how much the sample is drifting versus keeping everything at 4 Kelvin. So these, there's the map, you can see these, but it doesn't look great, so I didn't show it. But the magnon is very, very clear that it's much higher. The peak is about 450 wave numbers, but it's much higher in the areas where we punch, which would align with the theory that we have, that you have some out of plane magnetic component to the that's driving the change in driving the change in chiral state of the tungsten diselenide. So that's why we're picking up always one circular polarization. Whenever we say spin orbit coupling, usually we're talking about circularly polarized light. So the next thing is another thing that we're doing that ties in with microelectronics is we're trying to dope these 2D materials, and we're trying to dope them with low energy ions. This work is not low energy ions, but that's where we're trying to go to. So we have a facility called the Ion Beam Materials Laboratory at Los Alamos that's part of SINT. That facility, I'll have a slide towards the end. That facility has a tandem accelerator that can go up to, I forget the highest, but we were using it like 18 mega electron volts, and it can go higher than that. It's just basically you're putting alpha particles through a foil of a certain material, and then that'll give you, depending on the charge state, that'll give you much higher energy. So that's one capability that we have in the Ion Beam Material Lab. Another capability we have is an implanter, and that implanter is basically what industry has to implant silicon. So that's what we use for this study, is we're implanting, and we're implanting with, for this, we wanted a light molecule, so we're doing helium. We're doing just regular 4 helium plus, and we're implanting it at certain DPAs. So DPA is displacement per atom. 0.2 gets pretty high. It correlates to defect densities of like about 10 to the 13 or so. So it's pretty high. But what we saw when we did this is we saw there's some synergy because it's a really high emission at a certain value of DPA. This is 0.05 DPA. If we plot it in terms of the fluence and plot the change in the Raman intensity of the longitudinal acoustic mode, which shows up because you have defects. It's not an optical mode, it's just a longitudinal acoustic plus a defect will give you a Raman peak over the A1G, which is the out of plane Raman mode. And then if we plot the distance between these two modes, between the E and the A mode, which you can think of it as that gives us a measure of strain state in the material. This matches up pretty well, with the exception of you have this outlier in 0.05 DPA, which also aligns with this huge shift we see in photoluminescence intensity. This is all at 4 Kelvin. Well, nominal 4 Kelvin is probably really 7 Kelvin. But that's a nice kind of observational trend that we saw when we're doing that. We really want to push this to implanting. So we weren't successful in implanting, but we were successful in damaging the material while still retaining overall crystallinity of the material. You can think of it as a radiation response. If you have a material close to something that's radiating alpha particles, it will have this response. But I always like to show this because it shows kind of some of the benefits of working with the ion beam materials lab. We, when I first got to Lano, we started working with Rutherford backscattering spectrometry. It's a mass spectrometry technique where you can tell stoichiometry to within, you can tell stoichiometry to within about a couple, well, you can tell stoichiometry very accurately. The uncertainty in the stoichiometry that you get will be about 5%. So 5% uncertainty on like a 1% difference is actually pretty good. So we can't pick up isotope differences. We tried to do it. We don't have that resolution, but we can pick up differences in sulfur vacancy ratio just by hitting it with lower energy alpha. So the sulfur vacancies go way up to the point that you start out a little bit above 2, because when these are grown at Penn State, these are grown with about an 18,000 to 1 ratio between sulfur and molybdenum precursor gases. So it's about 2.11, and then it drops off as you would expect for the vacancy, but we still have this outlier at 0.05 dPa. So we don't know really what's going on with that, but we do know that you do have some synergistic effects. And so we said, let's use this as to show that we can do this type of material modification. We have control over it. You can see how nice this trend is. But let's try to look when we're talking about modifying the materials properties for doping, let's try to get some follow-on funding to do doping as we go to even lower. This is at 50 kilo electron volts, but to go to even lower energies. And so that we're looking for investment from the CHIPS and Science Act is a small part of it. But you can see how useful this can be as opposed to just putting it in the fib and like hitting it with ions. So the next step, I'm going to show you this pretty quickly because I want to get to the synth portion. But the next step is we're doing structural characterization with electron microscopy. So now this transitions to diffraction analysis mainly. And so what we do is we have in situ heating holder. We have a bunch of in situ holders, but me personally, I have in situ heating holders, MEMS-based heating holders. And we hit our materials. We're still using 2D materials for this demonstration, but we hit it with a probe that's patterned. The nice thing you learn when you do a lot of electron microscopy work is you can tear things out and change things. And so working with Berkeley, we changed the shape of the electron probe so it's not circular anymore. And you can hit the sample, you can diffract, and you can collect those diffraction patterns over a space to come up with grain statistics in 2D material. This 2D material, you can think of it, it's not exfoliated. It's grown by our collaborators in Korea on silicon dioxide. So it's not epitaxial. Grains are about 50 nanometers. So that's kind of the motivation for that. But I'll just show you some results. We were able to do work on tellurium, which showed that with the 2D material, one, we can get orientation, but with the 2D material, we can see the chiral structure. We see no net chirality. But we're able to make this material in a microwave reactor system. But the microwave reactor makes a bunch of different things. It makes flakes, 2D flakes. They're about 20 nanometers thick. It makes nanowires that we measured, and it wasn't just one of them. We measured a lot of them that were down to about 3 nanometers in diameter. And then it makes ribbons, things that are like rectangular in cross section, but maybe 50 nanometers. And so we said, characterization technique, why do we have to go with the textbook example of you can never do quantitative diffraction in electron microscope because uncertainties are like 2 to 5%. So we said, let's get that uncertainty better by using the new methods that we came up with our collaborators at Berkeley to do pattern probe and to do to apply some techniques from astronomy on registration of disks. So we do disk registration on the diffraction peaks and quantify that in the way that you would do on the X-ray diffraction. So obviously this doesn't look as sharp as X-ray diffraction. One reason is these are nanomaterials, so there's broadening. The other reason is it's not as clean of a way to do the measurement as X-ray diffraction. But we have these scans on like 5 nanometers of material, so much smaller localized length scale. So what we found, this is a Williamson Hall plot. For those of you guys who do refinements, it's just plotting in a certain way, plotting the full width half max over the Q vector. So this is the Q vector, and then the full width half max of each of these peaks. We can plot these, and we saw a nice trend that we didn't expect we could see with this method is the microstrain that you get. So the intercept and the slope, it gives you microstrain, and it gives you the well, mainly in this we're looking at microstrain, but the microstrain is different in the nanowires, the 3 nanometer nanowires, compared to the bulk, compared to the powder that we did X-ray diffraction on. But it trends from 1D to 2D to 3D, which means there should be some local relaxation in the 1D material to accommodate for that built-in strain. And so that brings us to circularly polarized light. So when you have helicity in the material, then there should be a degree of circular polarization. We picked it up with these nanowires. The measurement was done with our collaborators at Rice. It's not high, the degree of circular polarization, but it's measurable. And in the 2D flake, it's not there at all. And that there is chirality in the 2D flake because it's tellurium and it's a helical HCP crystal structure. These are helices. But you can see this lets me, that doesn't let me click on it. But if we scan across this, you would see the diffraction pattern change. The real breakthrough that we had was all of the talk on circular polarization in chiral crystals for tellurium wasn't measured, but we measured it with a nanowire. And then because we have these electron diffraction techniques to look at longer range helicity, which we measured to be about 50 nanometers, we picked up certain the degree of circular polarization difference that was slightly different. I think it was like the highest was 0.2, something like that. But it was much higher than expected. It's because that microstrain forces the structure to relax by torsion, and then that gives you the difference in left and right hand circularly polarized light that you can actually measure. And so that's what we're showing here that our artist did for us. So, and this is with second harmonic generation. You know, you have crystals that don't have symmetry. You can do second harmonic generation on it. So this is an SHG circularly polarized light experiment. So then we can do the same kind of work on these grain structures in 2D materials, looking at misorientations, looking at how strain happens in the crystals. These are nucleated over crystals. This is a monolayer, and this is the second layer that's growing on it. And we can get statistics on this to show that you can actually calculate in a statistical way the misorientation. So the 2D material, it's kind of expected that you could do this, but we wanted to show this because no one had really shown automated crystal orientation mapping from the electron diffraction before. So again, this is in collaboration with our colleagues at Berkeley. But this is really nice. I'm happy we got a journal cover out of it. But even more than this, because this has applications to structural materials like magnesium, we got the cover of the report to Congress for the funding program. So we're pretty happy about that. This is a messier problem. So this, I just want to show you an example of what we can do when we talk about structural materials. This is the kind of work that we'd be doing with the project that Professor Yakimin is working on. So magnesium, HC crystal, great for nucleating twins. Look, find a low angle grain boundary. This is electron backscatter diffraction. Take that grain boundary, cut out a fib section of it. This is what it looks like here. This is what the strain state looks like at 0 strain. These are magnesium oxide precipitates from which twins nucleate from. Take this and strain it in situ in a TM, and what you'll get is you will get a twin forming. So this twin formed. It's the only experiment that we got it to work. So this is like what we went with. We don't have any reproductions of this just because the experiment is so hard. But we got the twin to nucleate, and we got the twin to stop. So it nucleated, it stopped about 50 nanometers from the grain boundary. When we looked at the strain state, because this we're doing diffraction analysis, we look at the strain state. Overall, we can compare the strain state in the regular material and the strain material, and then look at it after we leave it for 14 hours. So you can see it, there's nothing there. You strain it, it's strained, and it relaxes a little bit and gets much messier if you leave it for 14 hours. This is an analysis of the entire diffraction pattern for the whole sample window that we're looking at. For this, you can see that, but if you look at the pixel by pixel, so at the 1 nanometer scale, then you can really see where the techniques that we look at are valuable. So the strain state, so this is XX strain, this is YY strain with respect to real space. So like Y is top and X is right. And then the crystal was oriented along 001 here. What we saw is we saw a strain state that changed in the X direction from compressive to tensile at the tip and then back to compressive. And then we're able to get the strain inside of the twin. This matches up exactly with phase field modeling, which from a mechanics standpoint is kind of a nice result. It's for one of our core BS programs that John Vetrano runs. So this experiment is something that the theorists were thinking about for more than 10 years, but just no one could do it because we didn't have the analytical techniques to make this characterization. But the fact that we can do this kind of work in situ, this is what leads to the mission relevant follow-on work that we're working on now. So in terms of conclusions for the scientific work, what you can see is, so I have my personal research, but also we have, and this gives you an idea of what like we as individual PIs are interested in. So I'm not showing from our collaborators, they have their own really great work. But for me, we're interested in isotopes. We showed first demonstration of that isotope effect on photoluminescence from this comes up with from band gap renormalization. We created a new method to do the spatially localized quantum light emission. That was, again, my theme of collaborations that was brought on by a suggestion from an Army Research Lab program manager who's now at Penn State, who set us up with Air Force Research Laboratory to initiate this line of work. We had the materials, we had the devices, they had the characterization technique. That led into a whole line of research. With respect to electron microscopy, we can now get local structural information at the nanoscale with resolution. This is reciprocal space resolution, because we're accounting for instrument broadening and instrument response function that rivals XRD analysis, but it gives information about the whole three-dimensional nature of the crystal, because we can collect all the different HKLs, which give us out of plane information. We've done a demonstration of orientation and lattice parameter mapping. So we say ACOM in the TM, and that code is active now, and those techniques are active now. We've modified the apertures in our TM to do that. And we have statistical understanding of the grain structure analysis in continuous 2D films grown on amorphous substrate. We do see preference for misorientation about 8 degrees. And then this I didn't show, but we have tunable thermal conductivity in 2D materials, which is kind of related to some of the stuff that I was talking about with Miguel. So the kind of the takeaway from this is we have physics problems, right? We understand, this is why I work with theorists. We understand from theory what are the physics problems, but we have to build new experiments to access those physics questions. And if you can do that while at the same time building something that's relevant for either industry or mission needs of an organization or a program, then you can have a double win. So that's where we try to do, try to work in that space. For our students, Alejandra, all the TM stuff, Alejandra's the best postdoc ever. She's now at Applied Materials. Teresa Kuczynski is my current TM postdoc. And then the irradiation work was done by Shaini Parida. She's a theorist, I hired her from Connecticut. Shuijing Wang, she also did the irradiation work with me and the R&D Materials Lab. She's one of our directors funded fellow, and her paper just got accepted today in NanoLetters, so she's really happy. It took a year to get it through. I don't know why. So we're kind of upset with NanoLetters. But she did really great work. Marshall Campbell is doing a lot of the low frequency strain Raman with me. He's a UC Irvine student that we hired for a year, and now we give him a sub-award to continue the work with his professor at Irvine. Hivo is a mechanics director's funded postdoc that I co-mentor. And he's the one that did the magnesium strain experiment. That experiment is extremely difficult. He's the only one I've ever seen to do that. And then my current students are Regen Parkey, who does the Raman modeling, and Micah Valen, who's doing some of the, who's following on with the strain Raman work. So very briefly, I want to talk to you about SINT. So what are we and what do we do? So we are funded by Office of Science. We get money from Office of Science to help you guys. Like Office of Science gives us money to help professors and to help industry. But industry, we require that they publish. And so sometimes industry doesn't like that. So we have less industrial use. I have 2 industrial users that I personally help. Our co-director at the Los Alamos side is Adam Rondinoni. He came over from CNMS, which is one of the other nanoscience research centers at Oak Ridge. I'm one of the deputy group leaders. Ricardo Marchel is our other deputy group leader. He came from bio division, so he knows the bio side of the house really well at Los Alamos. We're one of 5 NSRCs. So the NSRCs are located at Molecular Foundry at Berkeley. That's why we collaborate with them. Office of Science loves when we, as an NSRC, collaborate together now. That's probably one of the new things since you were there. They like that now. They don't make us compete against each other. So we collaborate a lot with Molecular Foundry. We're SINT, we call it SINT Gateway, is at Los Alamos. SINT core facility is at Sandia. The clean room, the best clean room ever, is the one at Sandia, at our SINT core facility. But writing user proposals provides access to both sites, and we're funded under one center. And then Center for Nanophase Materials is at Argonne. Center for Functional Nanomaterials is at Brookhaven, and then CNMS is at Oak Ridge. So these we like to say that they're different from traditional user facilities in that it's not like a fee for service. Like we don't charge you guys anything. We've had a lot of people come through. We hire high school students, we've had undergraduates. Mainly it's graduate students and postdocs, but then in the clean room, we even have some staff members and professors that come to do that work that they can't do at their institutions. Mainly we're working with academic institutions, but the nice thing is for the user proposals, and our acceptance is pretty high. And if we don't accept the proposal, we usually say why, and then have someone submit a rapid proposal and then help to get the proposal accepted the next time. So persistence pays off, but it's free. So for us, we want to create national resource. We're kind of the microelectronics center, national resource for nanomaterials integration. So making devices here, characterizing devices here at Los Alamos. We do spectroscopy really, really well. They do microfabrication really, really well. So today we have 4 thrusts. So we have 1 leadership team. So 1 team reports to Linda Horton. So it's not 2 separate centers. Ever since inception, we've always been 1 center, and we travel back and forth. Our scientists and our users travel back and forth between sites. We have about 60 scientists. We have 19 affiliate scientists. INV Material Lab is one of them. Our electron microscopes up at Los Alamos have affiliate scientists that work for us. We have about 40 postdocs and students that are funded by the SINT program, not by our personal grants, but by the SINT program. SND and LANL, and then we have distinguished affiliates, Barry for microscopy, Rajiv Kalia, who does a lot of AI work from USC, And Tony Taylor she's retired now, but she has an appointment and she has an office space in the laboratory for ultrafast materials and optical sciences, which is in our group. And they're very active. I see Rajiv at Sandia, I see Barry at both sites, and I still see Tony. Tony was the level below the lab director at Los Alamos. She's been a great friend to Sint and one of the original founders of Sint. So our scientific thrusts, we have optics, we have in situ characterization and nanomechanics. This is where my scientific research falls in. Our microscopy team is in here. We have soft biological and composite nanomaterials. Cryo-EM is in here with John Watt. And then quantum material systems, which at Los Alamos relies on ultrafast characterization and material synthesis. And at Sandia is a lot of the ion implantation and qubit work that they do down there. We have users from all over. As you could expect, they're basically the map is what the map of universities looks like in the United States. And we have some international collaborators as well. Like I said, we have a lot of collaborators in Korea. Publications are a primary deliverable. We mean that for us to get funded, we need to have a lot of publications. That's what BS cares about. Those of you guys with BES core programs know that your program manager only wants publications. So we give them that. Last year was our highest publication year at about 400. Importantly, we have a high impact metric of impact factor of 7, and about 36% of our articles that we publish are above that value. So we do high impact work, and then we also do larger volume publication work. So you can probably notice that trend in some of the work that I showed today. We have some low impact and some high impact. And we're an outreach tool. So we're Gateway for a reason. We bring in people, those people get hired at the lab in other locations. So I want to show you this ion beam materials lab very quickly. So this is the ion beam materials lab that Yang Wang runs, Yang Cheng Wang. It's an older facility, but it's a kind of a state-of-the-art facility for doing mission-related and metallurgy work. This is a radiation damage facility. It has a tandem accelerator where we can do alpha particle irradiation. It has a corrosion cell where we can look at corrosion like from radiolysis products. It has a 200 kV ion implanter where we can implant basically anything on the periodic table. And it has a new positron annihilation spectroscopy beamline on it where you can look at what defects are doing before they become bubbles. So for people looking at radiation damage, that's very important. This has a lot of SINT users and a lot of SINT user proposals and results in a lot of our publications. And a lot of people might think it's just for weapons research. It's not, because we fund half of the time, we have fund half of the salary for this center. And so this is a big draw for the metallurgy and structural materials community that the other NSRCs don't have. Berkeley doesn't do this kind of work. So just so you're aware, you can work with the ion beam materials laboratory. How we do it is by proposals. These are short. You write your NSF proposal, basically copy paste the abstract, and then talk a little bit about the work that you're going to be doing with the scientists, and that's all it is. It gets reviewed, and then we grant access to all of the facilities. So you don't have to write 2 separate proposals if you want to do ion beam materials lab irradiation, and then you want to work in the clean room. And so I'll leave it there, but just as a reminder, the way to start out with working with SINT is just to reach out to some of the scientists. Or if you're Professor Yakiman, you'll have me reach out to you because you have a very famous department head. So look on our website, it's sint.nano.gov. We just updated it this year. We went through like a major branding update for it. And so the capability pages are updated. And so mainly you can look at expertise for the scientists, and you can also look at tools of what might be useful. Like I mentioned, if you're doing interested in cryo-electron microscopy, that's on there. And they'll give you the contact of who to reach out to and send an email to. So I'll go ahead and stop there. And you can take any questions. And we're a few minutes over time, so if you guys have to leave, just let you know. Oh, yeah. The last part, how do they? So we weren't using the magnets to create defects. So we were using nickel phosphorus sulfide, the NaPs3. There's a couple others in that family of materials. I think you can buy them commercially now. Typically, if you want to know where we go for our materials, we get everything from HQ Graphene or from collaborators. But if HQ Graphene sells it, they're extremely high quality. So that we're using. We have other people that are working on better, like materials with stronger magnetization, like chrome iodide. The one that's working on that in SIN is Prashant Padmanabhan. He's one of our ultra-fast spectroscopists, but that he does everything in the glove box. He has a couple users that work with him on it. But for us, we wanted to be able to do something accessible in our lab. So that's why we chose the NiPs3. And then putting it together with 2D material, it doesn't create the defect, but it creates that effective magnetic field in the material. So that's why we were using it. Oh, yes, you can. Yeah.
My question was over your single.
Okay, so personally, me, no, but within SINT, we do have 2 staff members that are leading efforts for that integration. So there's a company, we're talking about a company, Ubiquity. There's a company in Los Alamos that was started by Victor Klimov that they do quantum dots. Well, one of Victor's former postdocs became one of our famous senior scientists within SINT. She's doing integration by putting quantum dots onto cavities, like the 2D photonic crystals, to create antennas. And they've measured like directional emission, and they can do communications with this stuff at a very low level, of course. But that's an integrated device. They're trying to do the same thing with the emission sites that we're making. One of those is like chemically functionalizing the emission site. Another is implantation. The motivation for the implantation work was exactly that, but it was like we didn't get any color centers. But they are doing it, and they are doing it from the perspective of device, like making an actual device. Now, because we're at Los Alamos, they're also competing with Victor himself, and Victor's doing not the kind of work that we're doing, but he's doing amplification on chip photonics with quantum dots. So quantum dots are kind of nice because they're basically the same idea as what we're doing, except you have a large artificial atom. It's large enough that you can have infrared emission from that atom, or from that like artificial atom. And so they're using that approach. We're using the 2D materials approach, but I would say that for quantum dots, they're maybe 20 years ahead of us. But yeah, that is always something that we talk about. And for that, we do the collaborations. We go down to Albuquerque to do the fabrication in the clean room.
Could you give us a little insight on like, possible advantages of these 2D materials for the color centers?
So the main advantage, and I talked to Air Force a lot about this, about why they're interested in this. The main advantage is they're on the surface. And if it's like 5 nanometers below the surface, there's massive attenuation. So the stuff that I was showing, like I didn't talk a lot about the intensity scale, but there's huge brightness level difference between indirect excitons, which a lot of like my personal work is the indirect excitons. There's a huge intensity difference between that and with the monolayers. So all the bright emission that's in the megahertz range, in terms of count rate, mine is in the kilohertz range. It's all from the monolayer materials. It's very bright. It's relatively stable. I would say, if you want to say what is the key difference of why diamond is better, diamond works at room temperature. So that's a key difference. So that's why we were pretty happy with getting something that kind of works at 77 Kelvin. But yeah, with the 2D materials, the main advantage is like we say, ultimate proximity to interface, like it's at the surface. Yeah,
much easier to use and to get it naturally. In the two-dimensional material, you get the material from mines, and then you just do exfoliation.
Oh, right.
Can I say something real quick?
Yes.
Could you go back to your credit, your acknowledgement, your group photos? Alejandro Londoño, your greatest postdoc ever.
Yes.
She was one of our students at Antonio. And so we're, very proud of the training that she got there, that at least it didn't interfere with her becoming greatest.
She was better microscopy than some of our microscopists. Her training that she received was very good. And that's for the students at lunch, I was mentioning networking matters. She was really worried that she was like, I don't know if you're going to select my application. But I was like, as soon as she mentioned that she was Professor Yakiman's student, I said, I'm going to get her for an interview. so like the networks matter. Like if we know your advisors, obviously, sometimes things can happen without networks. Like I didn't know anyone at Los Alamos. I want to work there. So sometimes that can happen, but most of the time is having those connections between your professors with different facilities or different collaborators that you've met at conferences or through the programs that you're funded in. She was always worried. I'm from UTSA and they only hire MIT, and I'm like, oh, we hire people. There are people who are good at things, and so she worked out really well. Yeah.
She's now making a lot of money.
In Silicon Valley, yeah. And she's not the only Colombian. So I think she's happy now. She was a little scared about that. I think she's happy in Silicon Valley. Because all the telecommunications infrastructure that's been built, all the fiber optic cables, it's all in the telecom bands. The key band that they're building now and that most lines are is C-band, which is at 1550 nanometers. So it's because you don't have to replace all the fiber optic cables. Yes.
Well, thank you very much.
Yes.